Hi there, welcome to your lesson on segments and angles within 3D solids. Look at this diagram we have here. We clearly have a cube-like 3D solid or a prism, and inside of it we have this bluish colored other shape that kind of cuts diagonally through that shape. So this is what this lesson is all about. Are you able to look at 2D diagrams of 3D objects, and does your brain allow you to visually see these things inside of them at diagonal angles and so on? Let's take a look, because for a lot of students this is a little tricky. Let's do our very best with this. Alright, so we are talking about geometric solids, and this is the lesson where we combine a lot of the formulas we've learned recently and geometric solids. Let's begin with this little introduction. We have the world-famous Louvre Museum in Paris, which was commissioned by the President of France in 1984 and designed by the architect I.M. Pei. Okay, well, the Louvre Museum is much older than that, the main building, but this glass pyramid in the main courtyard is from that time. This structure, which is constructed entirely of glass sections and metal rods, reaches a height of 21.6 meters, and it has a square base with sides of 35 meters. So quite the large pyramid, and it's pretty famous. Let's take a look at that and represent it with this sketch. All right, so this sketch is to represent this pyramid. Now, notice in this diagram we have a couple angles marked, and we can clearly see these kind of triangles that are within the pyramid itself, right? So this is angle 1 alpha, angle beta, and we can see that this line down the middle would probably be the height line of the pyramid, and these two other triangles, right? So this is the kind of thing we're going to be dealing with in these problems. Can you visualize where these triangles are in relation to the other parts of the pyramid? For example, this one has a hypotenuse that's along the side or the face of the pyramid, whereas this other triangle, its hypotenuse is the edge of the pyramid. Okay, and these are the formulas we're going to use. Formulas we've learned recently, for example, the Pythagorean theorem. We've used right triangle trigonometry, for example, sine, cosine, tangent. We've then moved beyond right triangles and used the sine law, which can be used for non-right triangles. We've used the cosine law for non-right triangles, and the other version of the cosine law. So all these triangle equations all kind of come together now inside 3D solids. So let's see if we can do this. Here's our first problem. We're going to do 3 problems, only 3, but they're a little bit tricky, so that's why we're spending a little time on these 3. Let's look at this first one. We have a cuboid. It has dimensions of 4 by 5 by 6, and we can see them here. Okay, it says find the length of the diagonal DF. So it even drew it for you. Okay, you can see kind of this triangle in red inside that cube, and we're looking for the length of DF. So to begin, I've drawn that triangle. That red triangle with the dotted line, I've drawn it here. And it is triangle DFB. Okay, you can see here, DFB. And it sits kind of diagonally within the cube. So now, what do we know about DFB? Do we know any lengths of sides or angles? Well, we definitely know this side here is 6, because this is the length of this side here, so this must be 6 as well, FB. Okay, 6. Do we know anything else? Well, no, because 4 and 5 are not part of that red triangle. Okay, so we're kind of stuck. We can't really work with this. We cannot find DF unless we know something else about this triangle. So I'll give you a hint. Is there a way to find DB? How can we find the length of DB? Okay, DB can be found by looking at the bottom of this cube. On the bottom of this cube, you can see that red line that's part of our original triangle, DB. It kind of cuts the bottom of this cube in half. The base is cut in half by that. So we end up with this other right triangle down there. And now you have to really imagine it by twisting it in your mind's eye. And it's this triangle, DBC, which I've drawn here. This is taken from the base of this cube, and this triangle is a right triangle because that corner C back there is a right angle, even though it doesn't look like it here, right? It is. So what do we know about that one? Well, we know this side is 5 and this side is 4. So with those two things, you should be able to use Pythagorean theorem to find DB. And once you know DB, you can go back to your original red triangle, this one here, and you'll know DB, and then you can find DF. So how about you follow those steps? Find DB, use it here, and then find DF. Okay, let's check. dB, using Pythagorean theorem, solving it like this, dB is the square root of 41. So now I put that back in here, and now I use Pythagorean theorem one more time right here. I'm solving, and I get that dF is 8.77. Okay, so that's how we approach that. All right, looking at two triangles and Pythagorean theorem in both. Now, question B says, find the size of BDF, and this means angle BDF. So look at here, where's BDF? BDF. It's actually this angle right here in that big red triangle that we've been working with. So how big is this angle? Can you use maybe trig to find it? Try it out. Okay, I marked another side here. Oh yeah, that's the side we just found, DF. Now I'm going to use trig ratio here because it's a right triangle, and I'm going to do the sine of angle BDF because that's the angle we need. So sine is opposite over hypotenuse, so 6 over 8.77. Do an inverse sine on that, and you find out the angle must be 43.1. Okay, that one was not too bad to start. Okay, we just had two right triangles to deal with and some trig and Pythagorean theorem. Not bad. Hope you made it through. Let's try another one. Here's problem 2. Now, this happens to be the same cube, but we have this other triangle drawn within it like this. So try to imagine how that one sits in it, also kind of diagonally within the cube. Okay, so it's the same one. I don't think this is labeled here, but this entire side is 6 still. Here's that 5, here's that 4. Okay, it says that M and N are midpoints. So M is a midpoint, N is a midpoint of each of those lines or segments. And we are asked to find angle NEM. So look at that, NEM. We need this angle in this red triangle here. So we need to find out some things about that triangle. Do we know any lengths? Do we know anything about that triangle? Because we can't find the angle until we find some other side lengths, let's say. Okay, that one's a little tough to start maybe, but since M is a midpoint, and we knew this entire length is 6, we know this must be 3. Okay, so now we know 3. I'm going to give you a hint. If we're going to be working with this red triangle, it would be nice to know the length of EM. It would also be nice to know the length of EN. So look at EM. Is it part of another triangle other than this red one? Well, it definitely is. It's part of this triangle here, EHM. So if I think of that triangle, let me label this first. In the last problem, we already found that DB, this diagonal down here, is root of 41. So that means this must be the same thing. Okay, because those are actually parallel to each other and they're going from the same two sides of the triangle. So we know one thing about that triangle. But again, let's find these other measures. So if I'm looking for EM, I can use Pythagorean theorem in this little right triangle up here in this corner. And I'm going to say 3 squared plus 4 squared, because we know this length is 4, which means this is 4, equals EM squared. So EM is actually 5. This length is 5. Now find EN in a similar way. Can you find that? Okay, so I just found that's 5. Now I'm looking for EN. And EN, yes, it's part of this red triangle, but it's also part of this other triangle right here that I'm tracing now. Okay, EFN. So EN is the hypotenuse of that right triangle. So EN squared equals 5 squared. This is 5 because it matches this side. And 3 squared. So here we go. Finding EN is the root of 34. And now we have, on the red triangle, we actually have 3 sides of it now. So we have a side, side, side triangle. Do you remember when we learned cosine rule and sine rule? If we have a side, side, side situation in a triangle, do we use cosine rule or sine rule? Well, you may remember that if we have side, 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 we're going to use cosine rule. So we can use cosine rule to find the angle we need, which is angle NEM. So here's NEM. Let's use cosine rule there. Can you set it up? Try it out. Okay, we're going to use the form of cosine rule. We're looking for an angle, so it looks like this. Put in everything you know. If we're looking for this angle, then the side that goes here in the cosine rule, the part that goes here, is the side across from that. So root of 41 squared goes here, minus that. And the other two sides here are your 5 and your root of 34 here and here. All right, I hope you remembered how to use cosine rule. And now let's calculate that. So take the inverse cosine to find angle NEM. And it's inverse cosine of all of that. Lots of stuff to punch in your calculator. I always recommend punch this in one step. Don't try to do part by part. Do all in one step. Do an inverse cosine and then enter a fraction on your calculator. Enter all that at once. And you should get this answer here. All right, see, I told you this problem's a little bit tougher. They take a little thought. They also take some visual and spatial reasoning here. So let's look at one more. Here's problem 3. Now we have a pyramid with lots of stuff drawn inside of it. Can you imagine how all those triangles are sitting in there? Try to visualize that. Now, what we need is, number 1, we're going to look for 3 angles. First one is the angle between the edge BE. Okay, so BE is this edge right here. So the angle between that and the base of the pyramid. So if you look at this edge and the whole base, the angle that we have between this edge and the base is actually the angle that goes from O to B to E. So here I'm drawing the triangle EOB. It's this triangle that sits here and kind of sits diagonally there, EOB. Now, what do we know about it? Well, we know this side is 10 because that's the height. And do we know anything else? I think not. So let's see if we can figure some stuff out. I'm pulling up another triangle here to help us get these pieces. Look at triangle, maybe this one. Check it out. CAB. Where's CAB? CAB. Okay, why did I select triangle CAB on the base? Look at CAB is that half of the base, that triangle there. I selected that because if we can find this hypotenuse of CAB, which is CB, and we know this is the center point, then we know whatever this length is, then OB will be half of it. And OB is part of the triangle we're looking at right here. So that's all connected, all right? So let's find out how long CB is. Can you do that? Well, first of all, you should notice in CAB, this is 5 and this is 8, because we can see here 5 and 8, and it's a right triangle. Let's find CB. Using Pythagorean theorem, you can find CB to be a root of 89. And again, once you have CB, you know OB is half of that. So OB would be half of root of 89. So now we know that. That means that that is that length here. Okay, in that original triangle we drew, which is this one here, we now know this length. Now that you know two sides, you can find an angle. And what was the angle we're looking for? The angle between BE and the base. So that's this angle right here. In the diagram would be this angle. We're looking for this angle here. Can you find angle B? All right, I can set up a tangent, opposite over adjacent, and now solve for angle B. You're going to do an inverse tan, and it works out to 64.7 degrees. Hope you figured that out. Now let's keep going. Question B says, find the angle between the edges EB and EC. So where is that on here? Here's the edge EB, the same one we were just looking at. And EC is here. Okay, so you have one edge here, one edge here. So you're basically looking for that angle on top there. And the triangle we're talking about is this big triangle that sits diagonally but across the whole pyramid. Okay, in that triangle, it's not a right triangle. So sometimes it's easier to work with right triangles here, right? Why don't we say, okay, that angle on top there across that big triangle can be split into two parts. And if we know the top one here, you double it and it's together. Basically, it's cut in half by OE. Okay, so let's take a look at how I'm going to approach this. CEB, that angle on top, CEB equals 2 times angle BEO. Okay, so CEB, that whole angle there, is twice angle BEO. Okay, try to imagine up there. Read that again and try to imagine what's happening up there. Now, if we can find BEO, we're good to go. And BEO is part of this triangle, the one we've been working with over here, this triangle here. So find angle BEO, which is this corner angle here. Okay, that angle is 25.3. Why? Because we already found angle B to be 64.7. And we know this one's 90 degrees. So we just do 180 degrees minus 90 minus 64.7, and we're left with this angle here, which is 25.3. You could have, of course, done some tricks to figure it out as well. But anyway, now CEB is double that, which means CEB is this. We just found that angle. Now, final angle we need is EMO. Angle EMO. EMO. It's this angle right here in this triangle here. How are you going to do it? Okay, there's that triangle I'm drawing here. Triangle EMO is here. We need the angle on EMO. So we need this corner angle here. What do we know about that one? We know this is 4. We know this is 10. Find this angle here. This is just a basic trig problem. Tangent works. Solve this, and you have that angle. Angle M is actually EMO. And we've solved everything. Great job. If you found those difficult, you're not alone. These are tough. Great job.